Hi, everyone. I'm Robin Phillips, the Executive Director of National RTAP, and I want to welcome you to our webinar on bus driver workstations, how to retain drivers through effective COVID modifications and ergonomics. Our goal is that this webinar provide you with information you need to keep your drivers healthy in the long term through procurement of safer buses and with superior ergonomics, and also during the pandemic short term, optimistically, careful shielding modifications. We would like to ask that you please introduce yourself with your name and location in the chat box, your organization you work with, that'd be great. And I'm going to review a few housekeeping notes before we get started. For audio, you can use your computer or one of the numbers shown on the screen and you'll need to enter the ID that's there. And if you have questions or if you have problems, please put it into the chat box if you're having problems with the audio. So we're going to be using Q&A at the end because this is a really long webinar that gets into a bunch of detail, and we would really like to get all your questions about this. Please put those into the Q&A. So there's a different place than the chat. Put those into the Q&A and do that throughout the webinar. And at the end, we've set aside a bunch of time to go over those. And you can be recognized by raising your hand at the end of the presentation. Our agenda today is an overview of National RTAP brief, followed by an introduction of our guest, Brian Sherlock, who will delve into the ergonomics and give us the technical details. And we'll have questions following the presentation. For those of you who this is your first National RTAP webinar, National RTAP is a technical assistance resource center funded through the Federal Transit Administration. National RTAP's overarching mission is to address the training and technical assistance needs of rural and tribal transit operators across the nation and to support the state RTAP or training programs. National RTAP's comprehensive set of free technical assistance programs and resources includes training materials, webinars, newsletters, technical briefs, peer resources, and innovative technology initiatives, and they are all free to our users. National RTAP e-learning is a portal that allows remote training online for rural and tribal transit operators and state program managers. Learners can take self-guided courses and access other materials. Managers can maintain reports and documentation. We are guided by a review board consisting of transit and state RTAP managers, and they provide feedback on our products and help us calibrate that to relevance for the people that we serve, you. So, Brian Sherlock. Thank you, Brian, for being here today. And last year, the American Prospect said to Brian that he's a hardcore geek with a fondness for deep dives into science and journals. Better he than the rest of us. Brian is a safety specialist with the Amalgamated Transit Union International, and he's worked as a bus driver in Seattle, a union safety chair consultant, and a member of the Federal Transit Safety and Advisory Boards, and as an executive board officer. I serve with him on the FTA Transit Safety Work Group. He investigated incidents of separation, employment separation, and causes of disability ending driver careers, and produced and provided this webinar as an in-depth discussion of sightline issues with driver workstation ergonomics and geometry leading to pedestrian deaths. We look forward to your questions at the end of this for further webinars on safety and the bus of the future.
Well, hello all. I'm absolutely delighted to be here with you, and we've got a ton of information, and I wanted to make sure and get you a quick overview of a wide array of issues and solutions. And so I'm going to just rip through here just to make sure you get introduced to a wide range. So fasten your seatbelts. This is going to be really quick. So Starting off with ergonomics and some of the opportunities there, there's some amazing amounts of industrial injuries and time loss in transit. I'm sure you've all seen that. And just looking at one subset of those issues, low back problems, there was a fascinating study done collaboratively with King County, in which Seattle resides, and they run the transit agency. So they collaborated with the agency and the ergonomics department of the University of Washington to do an examination of low back costs because they recognized that they were absolutely through the roof. So some background numbers, roughly 81% of bus drivers have had low back pain. It's 50% for truck drivers and only half of the bus driver rate for sedentary workers. And these are very expensive claims, average of 263 paid days of disability. So getting out there toward a year, and that's within Washington state. And the claim rates are roughly 4 times the norm. The bottom line number here that's just staggering and important to all of us is that when they looked at the costs of workers' compensation and other medical costs, it was 12.8% of all costs for King County Metro Transit. That's over an eighth of all costs just going into low back. So why? Well, we have this rather joyful looking German doctor here who volunteered himself as a pincushion and crash test dummy. And he's on a fluoroscope here, volunteering his life, or health, to x-ray himself while on a shaker table. And so they start with low frequencies here, and then they go higher. And as they get to the resonance of those organs, the organs start to store energy, like Galloping Gertie, that bridge in Tacoma, Washington, that went down in the wind. It wasn't the strength of the wind, it was what you see here. It was the storage of energy in that structure, and it starts to kind of tear itself apart. And this is why you have lots of gastrointestinal kinds of disorders in bus drivers. And of course the back problems as well. And I'll spare you a portion of this in the interest of time that goes into where they drilled holes in his back and put little flags in to show how his vertebrae were moving. But if you get hard up for a video on a Friday night, there you go. It'll be available in the PowerPoint. And it really starts to bring home the preventable extreme vibration loads that operators go through. So why in the world do they have these enormous levels of whole body vibration? And it comes down to a couple of things, and one of them is what's called the sprung to unsprung mass ratio of large vehicles like buses. And so that's what is the mass above the suspension versus the mass below the suspension. So as you go over a bump, the mass above the suspension has to push all of that hardware back down to the road. Otherwise, wheels and all of that bounce like basketballs, and then you can't steer. So they use the mass above to push it down. That's what delivers energy into the chassis and into the operator. So if we lower that mass down at the suspension, this problem starts to go away. This is the existing suspension, and here's a Conestoga wagon for comparison. It's all too similar with a straight axle. Here's how the Europe and more modern vehicles do it. All of your cars will have independent front suspension. Almost all of your pickup trucks and that sort of thing will have it. And that's what you see on the left. And that system is a ZF system available for heavy vehicles. And it cuts down half of the energy that comes up thrashing the operator. Then we can add in more intelligent seats like the one you see on the right, which is sort of the gold standard. It's an active seat with accelerometers and a linear motor, and that cuts down half again. So the 50% reduction in the suspension again gets cut in half. So this starts to ride like a very nice car, and it's a trivial amount of money on purchase. Now, for those who have cutaway vehicles and similar, You can make similar kinds of improvements with things like this system. It's a commercial system. We have no interest in it commercially, but it's liquid spring is what it's called. There are other slightly less effective mitigations, but this really does seem to be the gold standard currently. And it provides active control of spring rates and shock rates. And you see in the lower left the reduction in sway, which is a big deal, very important in rural areas specifically, because you have higher speeds. And Cutter, as many of you will know, did a wonderful study on the safety of cutaway vehicles in rural settings. And it was really kind of alarming. The higher speeds, the occasional blind turn, all this sort of thing, creates more mayhem, and the stability is really critical in those accidents. So you can see the reduction in sway. I did a test drive in one of these, and that thing handled like a good handling car. It was absolutely dumbfounding. And now on the right-hand side at the bottom, you see the reduction in thrashing of the driver and the passengers. This is a big, big deal, and most of this benefit goes to passengers. And we've all been in cutaways that were just brutal, and this solves that problem. Now, we've got some other opportunities to improve both accident outcomes and ergonomic outcomes. And on the left here, this is Geneva. And the bus you're looking at is the most common in the world. It's made by Daimler and Mercedes. And there are as many of these on the road as there are buses in North America. This is extremely popular, even in third world countries. The same model, equipped exactly like they display in worldwide transportation events, is 275 euros as a hybrid. And we're paying $500,000, $750,000, up in that territory for the same gear. So we're getting a lesser product for less money. We need to fix this. And by the way, the Federal Transit Administration has just selected us to design a bus of the future prototype. And this Mercedes is our benchmark, and we're going to meet it or beat it. And we can beat it in some ways. And vision here is one of the big ones. You can see there's no blind spot. I'll show you some scary blind spots here in a minute. The dash and steering are a module that is available in the US, and it comes back and sits in your lap. So the reach is just as easy as could possibly be. And there are stocks like in any modern vehicle to control lights, wipers, all of that sort of thing. You don't have to take your eyes off the road to use them. And they're all distinctive when you lay a hand on them, so you don't have to look away from the road. This is just good on so many counts. And by the way, in times of COVID, it's important that the driver in this has their own isolated, filtered, safe air supply. And they can be kept in a bubble of fresh air that prevents viral load from the passengers coming up and infecting them. And for hundreds of our members, it's been fatal. And we can do other things for the ergonomics, especially during procurement. On the right, you see TRW active steering system. There's several of these from different vendors, and they sense the torque you're putting to the steering wheel, and they work with you. It both eliminates shock energy coming back in through from the wheels, and it greatly eases the effort of steering, and does much more than that. It where large vehicles like buses, you have to pull the wheel back to straight. This will straight for you and remove all of that extra effort. I measured the steering effort in a transit bus on a basically straight route in Seattle, and it was 13,000 plus pound-feet for an 8-hour shift in just times when you're moving the wheel over 30 degrees. I think that's just a small fraction of the total muscular effort that goes into the steering wheel. But what that's equivalent to is a 100-pound person climbing 132 feet vertically up a rope using only their hands. So you can see why people have so much problems with carpal tunnel, rotator cuff, these sorts of things. It's really preventable if we think about it carefully in ergonomic terms and resolve these problems at manufacture. So how does that look sort of in the physics and the medical outcomes? This is, again, the work of that collaboration between King County, the University of Washington Ergonomics Group, and Seattle Metro. And you can see in the upper right-hand corner here, that image is the shock energy itself in a study done by Professor Peter Johnson at the university there. And the purple trace is the seat kinetic energy, and the yellow one is the floor. And so you see those two horizontal red lines. Those are when the energy on your body is equal to your weight, both upward and downward, positive and negative on that left scale. And so when the trace gets to one of those red lines, you're getting walloped with the equivalent of your body weight. So for a 200-pound person, that's a 200-pound slam on top of their weight. This is a big deal. The going through a chuck hole, you can see 2.5 Gs. So that 200-pound person has their 200-pound weight plus 500 pounds of shock energy. Now, and that's common. Just a good-sized chuck hole will do that. And this is in a municipal bus now. And in the lower right corner, the ergonomics department collaborated with the biophysics department, and this gentleman, Oluk, was able to get a half-dozen cadaver spines and subject them to exactly the force signature that was recorded in the buses in real-world conditions. And what you see is a vertebral end plate from the spine of a 20-year-old who donated her spine to science, unfortunately. And she had no pre-existing spinal damage, but you can see a stress fracture there in the bony end plate of the vertebra. All the spines were damaged by this shock load. On the left, this is a NIOSH survey that I took in Seattle, where I think we had 1,500 people playing along, and it's an extensive survey. You only use this one if you really want an absolute ton of data. And this shows the low back experience of people by seniority. The first 5 years are broken out in individual years, and then it's 5-year buckets from there to the right. And what we see is, as people come in at the left, they have a very low rate of low back pain or injury in the last 12 months. But that just explodes as you get to about the decade point. And it gets to over half of operators have low back pain or injury. And then by seniority, it appears to get better as you go further into your career. And ergonomists cynically call this the healthy aging effect. It's not due to people getting healthier with aging. It's because they're being disabled out. Now, that's bad for the employees, of course, but it's also bad for the bottom line for agencies. And this has been studied a few different times. What does it cost, specifically in transit, to lose a driver out of the driver's seat unexpectedly? And it's between 3 and 5 years of wages equivalent. And so when you multiply that across a 10-year or 15-year span, it starts to look like the value of the fleet. So these are staggering numbers, and it is luckily addressable through good engineering. Again, we can make these things ride like a good car and not create the spinal fracture you see here in the lower right. Now, more recently, I approached the Mineta Transportation Institute in California, really great researchers, and suggested that we redo that study and instead use a Nordic survey, highly recommended. It doesn't put you under an absolute ocean of data. And so we again looked at that population. I went out and assisted in the collection with the researcher so that we would get a high degree of cooperation. And almost everybody participated. So that was really great. And the take-home message is in the lower left-hand corner here. The average of the U.S. population, the NCHS study, is in blue, and the driver population is in red. And you can see there's just a horrific increase in musculoskeletal problems in the operator population. And you can see up above a number of different body segments. Basically, the higher the loading of the segment, the more dramatic the effect. Also, there was a lot of other surprising variables. And as you see at the bottom of this chart, the males are in blue and the females in red. And females have a much tougher time ergonomically and musculoskeletal disorders, probably due to being slightly less robust in the musculature and skeleton. And part of it's weight. We were talking about sprung and unsprung mass before in the suspension and all that. Same thing goes on here. If you take a heavy guy and put him in one of these suspended seats, a regular old bus seat, and compare them to a light female, for example, or a light male, the little person jiggles away like mad, and the heavy person damps the motion of the seat and has much less total kinetic energy going into them. So there's some pretty dramatic effects here. And again, with some fairly straightforward engineering, we can eliminate this variable as well. And so when you look across your population of employees, you'll often see they get out in this 10, 15-year point and their rates of absenteeism really skyrocket. And they'll be out on one problem, and then it'll be another body segment, and it'll be another body segment. I didn't present the data here, but that profile you saw in the low back, where it's sort of a bell curve, that same profile is present in the experience in all body segments. And so folks aren't just sick, lame, and lazy. They're getting pounded on at about the same rate across all body segments. And so this Dutch study looked at how do they do when in terms of absences, and zero in the middle of this graph on the bottom axis is the date where they go out on disability. And this looks at a year either side, or 12 months total. And you can see in the early years, they're okay, and then the absenteeism rapidly rises, and then they're gone for a period, and they're next revisited in a year, and their attendance is right back down to where they were before as they move into an entirely different job. So people aren't just sick, lame, and lazy, they're getting pounded on. So there's some other things we can do to mitigate this issue, and maintenance of the seats is one of them. And I know this is a real bear for agencies because the seats really take quite a pounding as well. It's sort of surprising. And so the seats collapse like you see here. And we all know that sitting with a wallet in your pocket is a bad idea. But imagine the outcomes from this kind of elevation change from one side to the other of the seat. And this happens because the foams that are used, and the best of foams for this purpose, is good in compression, but not good in shear. So as we slide in and out, we tend to tear up the foam. So on these cutaways, the side toward the driver door will collapse first. And in municipal transit buses, you slide in and out from the passenger side. And so this pattern will be reversed. But it's very important to correct this because, again, the cost of these back injuries are really, really high and much higher than the cost of replacing the foam. So I was curious about what the rates of deterioration in the foam were. So I did this little casual study. What I did was I would jam my thumb into the foam at that point where it's deteriorating most. And early, I couldn't get my thumb down to the seat pan beneath the foam. And that's about 5 centimeters, something on that order. And as far as I could jam my thumb in there before my thumb gave out was 3.5 centimeters. So that's what you see at the left side of this graph. But in 6 months, we were down to only 2 centimeters of foam before I would run into the seat pan with my thumb. And by the 1 year point, we're down to 1.5 centimeters. That ain't much. And we start having real problems because the seat pans tend to have contours in them that create shear stresses in your tush, basically, and can nail your sciatic nerve and cause other problems. So highly recommend replacing the seat foam in buses that are used 12 to 16 hours a day at the 6-month point. But do it by measuring. This is a little difficult to do at first, but your folks can get to where you can easily do this casual examination without expensive hardware to test the foam. And a 1 year in commercial use is really too long to wait. But there you go. So that's the ergonomics. Another big issue that first got me into some real hardcore work for the union in safety was visibility and killing pedestrians. And this is a real clear example of why it happens. This is an Orion. I use them because they went out of business. I'm trying to work with the other manufacturers, so I try to not directly call them out. But you can see that I had to step to the right to see the driver in the seat, even though I'm very close to the bus here. You can see why. On the left side of the vertical pillar here, you can see a black rubber seal. That's illegal to use in regular passenger cars and trucks because the windshield can easily come out and eject passengers. And we've got standees, you know, this is not a good idea. It was done to somewhat understandably try to reduce the time it takes to pop out the windshield and pop in another. And it can be done in 10 minutes flat. But if you glue the window in, as is required in cars and trucks, you can get rid of that visual obstruction. And you can, by gluing the glass to the outside of the pillar, and you can actually, the labor time it takes to do it is real similar, but it does have to sit overnight and the glue has to cure. So there is a slight delay involved, but it helps free up an inch or inch and a half of width of that pillar, and it's critical. Then you can see similar obstructions to the right of the white pillar element. And of course the mirror, that just has to change. But you can get this entire structure down to narrower than the space between your eyes, so that there's one eye or the other able to see every angle and there is no blind spot. For vehicles without airbags, this is specific to them. We could discuss airbags and how to deal with that issue separately. But we can get there. And the engineer of this bus, Heinrich Mueller, worked for Daimler, real good guy, stoic German engineer. And I was on a procurement test drive with him and took a little video camera, a tiny little thing, stuck it under my chin as we made a left turn. And the entire street we're turning to disappears behind this structure you're seeing. And I took it over, showed it to him. He's a sharp guy. He instantly got that this was a lethal hazard and was horrified. We went through what I'm explaining now as far as the mitigations. And he came back, next time I saw him was about 2 weeks later, and this stoic German dude is jumping up and down going, I did it, I did it, I did it. And for $300 a bus, just under that, he was able to do away with this, get it down to less than the interpupillary distance for that small amount of money at the time of manufacture. So what's this look like from the driver's seat? This is the same kind of bus. And you can see this pedestrian under the red arrow. I put perspective lines in between his feet and the distant feet, and from his head to the distant heads, and then copied him like a chorus line. There are actually 3 streets coming into this very large intersection in Manhattan, but they're all gone. This is a very large intersection, so this is an unusually large area, but it shows the scale of the angle. And here it is from above. The bus was that at the location of that white block that has a red line around it. And the blind angle is the extent of that bracket. And see that orange cab? That's a full-size Detroit cab. And it just shows you the monumental scale of these blind spots. And if you just go sit in one of these vehicles like this, you're going to be impressed with the vast amount of glass. The eye-brain system is designed to fill in blanks like this. It was critical for our survival. And we don't have time to get into it. It's a really fascinating question. But if you just sit in them, you don't tend to detect this. So it's understandable why we ended up here. But as you look at them like this, it's a horror show. So what do we do to get rid of it on the side of the bus? The front of this vehicle on the left image is to our left. And there's the window seal that we plan to get rid of. Thank you very much. The green is fiberglass, and it's larger than the frame element that holds up the roof. We're not suggesting reducing the size of the frame. In fact, I want it increased. But you can do it in a way where the main axis of the frame is on line with your view of it. So it doesn't have to get wider in order to get more than twice as strong. That's a side issue. But the black elements here with this red bracket saying unnecessary, that's just the side window assembly. And there's got an aluminum frame that slides back and forth with the window. It can be just the glass like it is in every one of our cars. And that's what you see on the right is an attempt, this is a new flyer, an attempt to quiet my yapping about this. And good on them. They've made a big improvement here, just the glass sliding. We can go even further. As far as the middle element of that black wall, the emergency exit, that really isn't needed here. It's essentially never used. Decade after decade, no one will go out here. There's so many other available exits. And in that right image, you can see that you'd have to climb through this, over the seat and the steering wheel and fight with the seat belts. And then you've got to fight with the switches and the door handles and all this nonsense over by the window. And it's not a full-size emergency exit, so nobody ever uses it. If we want to make up for removing that capacity, give drivers an emergency hammer so they can take out the windshield. They're never going to have to do that. They can almost always walk out the doors in municipal transit kinds of settings, or out the numerous other emergency exits. So how do we deal with mirrors? Well, luckily that is possible, in cutaways or large buses. This is a mirror set I came up with for Seattle, and they implemented it. They went from an average of 2 pedestrian fatalities a year to none for a few years. And the principle of this thing is, instead of having an enormous mirror, the left side mirrors, these large things, were actually designed for the right side, and then they got put on the left to make it look symmetrical. They make sense on the right. They don't make sense on the left because of how far we are from the mirror and all of that. If you go about it by asking, what do we need to see and how can we best do that without impacting sight lines, you end up with something like this. The lower mirror is purely below the window opening. And so that enables you to drop the mirror quite a bit further, and then just don't make that upper mirror larger than it needs to be, because the one you're looking at shows you from the front wheel contact point to the horizon. How much more do you need to see? The one below shows you right up to where you can see out your driver's side window. So everything's covered, and you can see the pedestrians will be above the mirror. So what do we teach operators in order to mitigate these problems? Because everybody recognizes big vehicles have big blind spots. They don't need it, but they do have them. So we teach people to do a square turn at walking speed and a bob and weave in the seat. Now again, the left side of this image, just to the left of the pillar, in most agencies that will be either completely or partially blocked by the mirror. This one, the mirror is just below the sight lines. And what I'm going to do here is a square turn at walking speed. So I'm going straight, I'm going at walking speed, and oh my goodness, we've got a problem. Well, actually, we've got an amazing problem. And most buses, it's over twice this bad. Now, why did that happen? It happens because of the way intersections are designed. The pedestrians are going straight. That's where the crosswalk is. They're going at walking speed. What am I doing? As instructed, I'm going straight and I'm at walking speed. So that sets up a synchrony between the pedestrian motions, then the motion of the blind spot. And so that can track them even as you start making turns. And I don't have that video in here, but and we could go into more detail and show you examples from serious accidents that this can track very dynamically. So you see this guy here on the left, he's our crash test dummy for the bob and weave. I'm sitting low and forward, and you see the driver mirror down here. Because I'm sitting low and forward like a shorter operator, you can see that mirror. Now he gets in behind the pillar, and I'm going to lean forward against the wheel, and then you notice the camera go down. I'm actually crunching over the wheel. I'm really going for it, and I couldn't bring him out from behind just a pillar, much less a pillar and mirror. Now look at this on the left. It's like a clown car. Isn't that amazing? So now it's clear it's time to go, right? He's a dead man. Because as we start to pivot to the left, he's moving from our right to our left. So he would be tracked by the blind spot if we went ahead and made that turn with that geometry. And there's a number of geometries that create this symmetry, far more than you'd ever expect. Pedestrians can cross in either direction across that crosswalk, and depending on the speed and geometry, they can be hidden both ways, and we have both accidents fairly frequently. So this also happens on the right. I was driving a bus, and I pulled out in front of a buddy of mine driving another, and like that, I couldn't see him coming, and like that, it was a 60-foot bus I just pulled straight out in front of, and I was really paying attention. And you can't bob and weave with a blind spot that's that far away and really impact it. And I'm the bob and weave king here. I did a lot of fatal accidents and looked at this problem in detail, and I couldn't overcome it. I thought I'd had an absence seizure. There had to be something wrong with me that I didn't see this coming. So I went and did these experiments, and you see the outcome that there's a problem over here. The good news is we can have doors that are fully compliant with the legal requirements and are nothing but glass. And the cutaways have similar problems. I got this gentleman to stand on the left image where he's mostly obscured, and he's within one step of the bus. And he did one step forward here to be seen in the right image, but the frame elements here don't have higher load requirements than the bus. And we can get rid of a lot of this trash. You can see the rubber seal around the window. See how wide that is by comparison to the total pillar? And there's a bunch of plastic there that we don't need. And you could get that right down to small enough to where you couldn't possibly hide a pedestrian and retain all of the frame integrity. And we need to collectively get together and demand that manufacturers do better. Because these things, you feel like you're driving a tank or something with all the mirrors and frames. We can do better on all of that stuff. You feel like you're looking out of a little periscope. I've driven them. It's quite challenging. There is some great news coming out of Europe, although it hasn't quite come here in a big way. Some of the Vision Zero stuff has, and that's great. But London, they've got a new vision standard for large vehicles. And so they're requiring high visibility vehicles. And our buses couldn't get into London now. And this fabulous study at Leeds that shows that in the lower left graph here, the actions all where you see the red arrow. There are 2 bars on the left and 2 bars on the right. The 2 on the left are for high visibility and standard cab. And that's for an undistracted operator. They're paying attention to business. On the right, you have the same comparison of the traditional and high visibility cab. But notice that that distracted operator in the right 2 bars, they're looking down at the speedometer, whatever it is, they will only strike pedestrians half as often in a high visibility cab as an attentive operator in a standard cab. So again, a distracted operator with good vision will be half as likely to strike a pedestrian as an attentive operator in a standard cab. And this is because we have just enormously sensitive peripheral view detection of motion. We all know how people way off to the sides of your gaze will be just abundantly clear to you when they move. And so this accounts for this surprising outcome. But it's a great outcome, and we can make it happen in all of these vehicles. How hard is it? Well, this is a bus from the 60s, the old GM fish bowls. No blind spot, same basic structure holding up the roof and all that sort of thing, but there was no meaningful blind spot. Every element here was narrower than the space between your eyes. And just as if you hold your hand up straight in front of your face with your thumb pointing at your face and move it from side to side, you notice you'll see a shadow of your hand and then a good image of your hand. That's what's coming into one eye and the other eye. And your eye-brain system fills in the blanks, and you end up with no blind spot. You detect every angle while you do that. Now face your palm toward your face, and now you'll have a blind spot wherever you put that hand, and the hand is wider than the space between your eyes, and you can't repair that loss of information. And buses, by the way, from GM, this manufacturer, clear back in the 20s. As far as the windshield, they had these tiny little blind spots because of human factors, engineers being at the table when they took out a white piece of paper and started doing the work. Here's how it looks in, this is Geneva again. This guy is grinning like a Cheshire cat because I'm bitching about our shitty buses. Pardon me. My apologies. And you can see that there are no meaningful blind spots. You couldn't hide a pedestrian here. A couple of other things to note. Again, that dash and steering column sits right in his lap. No problematic reaches. If you notice the side window, it's cleared electrically, and the windshields can be the same without the lines. The way the side window drops down at the front, you can have a really fairly huge mirror, ridiculous size, and drivers can still see over it. So they're again using this mirror that's mounted at the just above the horizon. It's a single large radius convex. It's a great idea. They simply don't use flat mirrors, and I think we should adopt that. We have an archaic standard. I do like the mirror down low for the ergonomics of shorter operators who have to look up, excuse me, at too high an angle too many times. Most agencies teach operators to do that glance every 7 seconds or so. And if you try it and look at the significant upward gaze of short operators, you won't want to do it for a full minute, much less many hours. So here you have it, the European example, and this is what we're going to meet or beat with the prototype bus. And on the right, you have all too common in the US. And boy, the $300 saved just isn't worth the lives. So rushing on to the next one, security, and this is security from COVID and from assault. And what you see here is the common barrier. It's almost ubiquitous in Europe. It's by an outfit called Vision Systems. Again, no commercial link or profit. This is just simply calling out the best of the best. And there's a slight longer front overhang in these vehicles because they thought about barrier design when they drew up the bus. So to get the barrier to where it's effective, like you can't reach around it and it's out of your sight lines to the windshield and right mirror, it does take a little tiny bit more room. And this is a Dutch door basically. You can see there's that solid black base. And the glazing comes up out of that. You can see there's a slot in the left image. Whoops, sorry. And touch screens can be a pain sometimes. So in that pillar on the left side of the barrier, there's a pneumatic piston. And so it normally takes 5 seconds to elevate or lower the glass, just like in your car. But if somebody's strangling you or stabbing you, and these things do happen, you can hit an emergency button and that window is coming up forcefully and rapidly. The assault will end, and the strength of this glazing, it takes 550-pound pull to break it. That cutout at the top corner isn't a broken part. It's there in order to integrate it with the bodywork above the window. Oh, by the way, notice that the fare box is behind the driver. Thank you, God. We need to get those things out of the driver's space. About 65% of assaults have something to do with fares. So let's just get it out of the driver's space. You generally can't get blood out of a turnip anyway. Let's just avoid the mayhem. Now this is about the sidelines. The photograph is taken from the right front pillar, and you can see as you look from the yellow mark at the bottom to the driver's eyes, the sidelines to the entire windshield are to our right here, to the right of the barrier. So there are no reflections impacting views ahead. There is an impact like with other barriers if you try to look out the door. But with this glazing that goes up and down, you can mitigate that to a certain extent. And if somebody rushes up to do you in, you can hit that emergency button and get back to a secure environment. And by the way, it's quite a long reach around these barriers. So you can't just reach around and clang somebody like you can in all North American barriers, or with the exception of a vanishingly small number. And they're from Europe, by the way, the ones that are totally secure. Now, this barrier's really quite cleverly thought out. It has an electromagnetic latch that attaches it to the dash, and you can swing the barrier open and attach it to these stanchions that are commonly between the door leaves in Europe. They use bigger doors so people can enter and exit at the same time, greatly reducing your dwell time in zones. This is about the best thing you can do for your travel times and reducing them. If you've got a tough route, and we all know what times and what routes are problematic, you can heat map it or just everybody knows. So you can latch this barrier, raise the glazing, and you've got a secured emergency exit. And in a lot of your rural communities, you won't need this, but boy, if you do have any security concerns, this simply can't be beat. And it's got whatever you want on the inside of it for storage for the operator stuff. What a concept. And by the way, these even come, if you look at the right-hand image on the right-hand lower corner, see that little glove box in the dash there? That's actually a cooler for the driver's lunch. So you don't have ptomaine or something from sandwich going bad. And on the left, you can see that you can add supplementary panels here, and you're safe from COVID and all the rest. And if you look in the left image, to the left and behind the operator, there's a compartment you see open in cross section at the highest point of that drawing. That's where the driver's HVAC is, and you can, these all supply fresh filtered air to the driver. Many countries in Europe require it, that employees, regardless of setting, have fresh air. And in this setting, that means filtered. So that greatly reduces our high loads of respiratory infections and all of that, which have, again, a huge impact on time loss that's excessive in transit. And just some filters can take care of it and keep all the viruses away from the operator. So here's what the glazing or the barrier looks like. It's that red line. This is a 95th percentile male, 5th percentile female, plenty of room. This is a very inviting space. This is how they do it in London, for example. They wall off the driver, and it can be a fairly inviting looking modern space. Doesn't look like an armed camp like so many of our barriers create the impression of. So rushing on to COVID-19, many of you have seen this unfortunate Facebook video from one of our members, Jason Hargrove. He had a passenger get on, they're fairly close. They cough multiple times straight at him, don't cover their mouths. And he got out at the end of the line and had this really frustrated rant. And in under 2 weeks, he was dead. And with hundreds of transit employees have been lost to COVID. And he's just a particularly poignant one because here he's telling you why he dies. So what can we do about it? First, we have to recognize the scale of the problem. There were some issues with CDC NIOSH and recognition of aerosol transmission. Part of that's historical and the way the science had evolved, but it's abundantly clear that aerosols are probably the leading cause of transmission at this point. This is a bus where a third of the people got infected. This is from a Journal of the American Medical Association peer-reviewed article. Highly recommended. The index patient, the first one that came in infected, is in the middle of the left side in row 8. See, it says IP. And look at the distribution of those other infected people. And this is 2 minutes or 2 trips of 50 minutes each with assigned seating for people going on a trip. And there was no statistical difference in probability of infection throughout the entire vehicle because the recirculation of the air and the absence of really great filters in most transit buses. And so there are other proofs of the transmission directly in transit. The one at the top, it was 1 trip and 16% were infected. The middle is the one we were just talking about. That's 2 trips and 33%, twice the number, were infected. And at the bottom, a real famous case you'll probably all know about. It was a choir in Skagit County in Washington State, and they were singing for 150 minutes, and 87%, the overwhelming majority, were infected. And again, singing, the louder your utterances, the more viral shedding. So that is a factor here. But what I'm trying to get at is the importance of the duration of exposure to aerosols. The inoculum, the amount of viral load you have to get in order to become affected, is generally not just a one and done, unless you have a large respiratory droplet that hits your mouth, your eyes, or your nose, inside your nose. It generally is more diffuse, small particles, and it takes a while to get infected. It's probably something in the order of high hundreds of viral particles called virions, or in the low thousands. It's in that range somewhere. CIDRAP is looking at that question. Hopefully they'll have an answer for us soon. So there's some really contradictory or confusing, counterintuitive airflows going on in all of our vehicles, whether they're cutaways or municipal transit buses. And you'll see that in the upper left-hand corner. I took this image while going 30 miles an hour to our right, and you can see that it's part of a video, so you can see this going in real time. I didn't embed the video here for brevity. So the transfer is blowing forward, meaning the air outside the bus is going forward faster than the bus, and it's about 1.5 times bus speed. And the transfer is blowing away from the window. There's a low pressure zone out there because the air approaching the front surface gets shot out to the sides, and then the squarish front corners that save a couple of bucks again in construction. Very few. The corners are too square for the airflow to turn those corners, so it separates, shoots out to the side, leaving a low pressure zone right behind the front surface all the way around. And so, as in the bottom left corner, the airflow in the bus goes from back to front and exits out just behind the front surface, meaning the viral loads of your passengers are dragged forward and exit past the driver, who's in there for a lot of hours. This is a serious problem. This is also why you get exhaust intrusion into the vehicle. How in the world does the exhaust that goes out of the roof at the back, and you're going forward, how does the exhaust get in? Well, that's the basics of it. And now, a little on the fluid dynamics here. This is a thing called a flume. It's a flow of water that goes from left to right without any turbulence, unless there's something in the flow. And so there's a square on the left side of this image, a white square. That's a bluff body, a blunt object like a bus. And they inject a dye in the front of it. And you can see how the dye separates out to the sides. And then there's this huge wake called turbulent entrainment. See how it forms these pairs of cyclones? Really interesting. It's beautiful stuff. Now in the upper right, that object has rounded front corners. And you'd be surprised how little rounding it takes to get this same kind of an outcome where downstream there's little or no wake. Now you could take that object and you could cut it vertically in the middle, and you'd have an area of turbulence behind it, but it would vanish in much the same fashion as you see here. As long as those front corners are extremely rounded, it can be very blunt in the back, and that's what you see in high efficiency vehicles like a Prius or something. They have very surprisingly blunt back ends, but very rounded front ends, and they have extraordinarily low turbulence. So I did an experiment at the University of Washington Fluid Dynamics Lab. You see that in the upper left-hand corner. Thank you very much to Professor Robert Breidenthal, who's done a bunch of work in transit for us. This was our first collaboration. And I did this model of a Gillig Phantom. We injected dye through that little tiny pipe you see coming in from the upper left-hand corner, that red dye. And so you see the dye is shot out to the side, and then it's pushed backward by the flow, and you get that same entrainment of pairs of little cyclones. And they're counter-rotating, interestingly. It's just a beautiful process. And that low pressure zone drags the boundary layer right next to the skin from back to front. Now in the back, I just mentioned the exhaust intrusion. The bus is that, labeled bus, is going to our left. I just gave you a little slice of the back of it. And just behind each corner of the bumper, you can see the eyes of two hurricanes. Again, they're counter-rotating. Everything between those two eyes is moving toward the bus faster than the bus. So we gather up dust and debris off the street. You notice how dirty they get inside. This is one of the big mechanisms. And part of the exhaust gets dragged in, thrown up against the back of the bus, which isn't well sealed, and has a partial vacuum. That gets dragged inside, and then you have all of these problems of COPD at nearly twice the rate of the rest of the population, according to NIOSH, and exhaust intrusion and all this sort of thing. And we can solve these aerodynamic problems, by the way. We solved it for that Gillig. So this had me in a real fit as we could see that this this pandemic was going to come here. It was simply too big in China to be contained. And I was really in a panic because I knew we were at the exhaust end of that stream of people shedding virus. So this is what I came up with as a solution. In the upper left, you have a experimenter in working with a biohazard containment cabinet. And you notice it's open, you can reach right in there, but they're safe because you control the direction of the airflow. And we can do this in our vehicles. And on the right, I show the hierarchy of controls. You probably all heard about it. The best is at the top. You eliminate the hazard, and hopefully we're going to get there with vaccine. Substitution, you start hauling mannequins instead of people. No, we can't do that. We can get to the middle level, though, engineering controls. And we can control the airflow, we can put up barriers, and we can provide this quality of containment you see on that upper left image. Administrative controls like end front door boarding, if possible, establish spaced seating, similar kinds of controls. And then at the bottom of the hierarchy, oddly enough, PPE, the thing we think of grabbing first, is that it's the least effective because it still keeps you exposed to the hazard. It's still vital. We need PPE, and hopefully we'll get it soon. But right now I know it's quite a challenge. So how do we do it? All of our vehicles except Gilligs, which have no fresh air. I cannot tell you how, I don't have anything civil to say about that. But we can, in most of our vehicles, bring fresh air in through the front and create a barrier, and that becomes a bubble of fresh air around the operator that can then be shared to ventilate the space behind. And everybody's better off, but the employee with the long hours of exposure can now be made fairly extremely safe. As long as they're in that bubble, they're extraordinarily unlikely to come home with COVID because they were driving a bus. So you can set up, this is the easiest kind of a format of smaller vehicle to deal with, where the passenger door is behind the two front seats, and you just wall that puppy off with some vinyl sheeting, or it could be old grocery bags, it could be anything. Just casually get that in there ASAP. And with the front air being fresh, it creates that bubble. It can leak, just like what you see here. It'll leak underneath the bottom of it. You really want to arrange any leakage, and I'm in favor of some leakage, at the top, because you don't want to loft the fomite, the respiratory droplets that land on the floor and dry. It's easy to loft them once they dry, and you don't want to do that by having the leakage at the bottom. Not a huge issue, but just if you have a choice, have it leak at the top. Cutaways more often look like this. And again, you can solve the problem. Now, this does leave the huge gap between the windshield, barrier, and dash. So we need to close that off, these areas here. And also, again, there's a gap at the bottom, as you see in the right image. Put that gap up in the top. A separate FTA-funded project we did, I pulled this together at Virginia Tech, and they've come up with a barrier design for buses that's back behind the operator so it doesn't intrude in sight lines. And we intentionally left a gap at the ceiling. And we left it over the passenger side so that wheelchair passengers can come into that space, and they'll be in the flow that goes past the operator, past them, over the barrier on the right side. So the gap is on the right with intent, and that ventilates the space behind, because we need all the ventilation we can get. And we have to be very careful. Another one of the counterintuitive things in the airflows in buses is what you see on the left. If you have a defroster blower going, for instance, that light blue line is the vortex. It's called a bound vortex. It just sits there and spins. And as it does so, it drags in air. It's called entrainment. That red arrow along the floor, it'll drag that up and into the driver's area, bringing the viral load to the passengers. And that will also occur because of the blowers in the dash. It'll drag air around the front of partial barriers. and it is a real bad thing. And you've seen that airflow on the lower right-hand side. Here's what most of the barriers look like in North America. Excuse me. They're a partial barrier, and this just doesn't do the job. It does protect against respiratory droplets, but that really isn't the whole story here, and not the predominant exposure of operators. It's better than nothing, but A, we shouldn't be bringing people in the front, and B, the barrier should be complete. So that red area that's bigger than the surface area of the barriers, all that should be sealed off, and it's not as hard as you'd think. You can take a piece of flexible vinyl sheeting and just tape it to the ceiling and have it come down as a drape, and that could come across and down in front of the barrier. So it would be cut vertically at the leading edge of the barrier, and then the portion that remains from where the barrier curves around over the fare box and drops down to near the floor, that can be a skirt that's attached, and again, it can just be tape to the bottom of the door here, and so that will seal that area well enough, as long as it goes over to the right front pillar or up to the windshield itself. I would urge that it should go across the dash and attach to the A or B pillar. They're named sequentially from the front, the A pillar, the B pillar, and so forth, going backward. You can really keep the drivers safe as long as they've got fresh air coming in the front. If they don't have fresh air, then you slap a high-grade filter on the air intake for the heater defroster in front, so that's what you have to do in a Gillig. But again, if you have the driver walled off and they're wearing a mask, they can have a high grade of protection. It's not nearly as good as if you can have fresh, where they can be virtually assured of going home healthy. So the key is you've got to test these things because the airflows are very counterintuitive, as you've seen. And you can do it with a cigarette, as you see in the middle. You can get various smoke sources like you see on the right. But what I really urge is just take a piece of yarn or something very light, like the telltales you see on the sail on the left. Those are used by people doing sailing. You can attach that to a coat hanger and just go around all the way around the workstation, and you can figure out which way the air is flowing. And you can do this throughout the vehicle to examine airflows. And just use a coat hanger with a piece of yarn on the end of it, and the lighter the better, and you can build up a mental image of these flows really well. Be sure and do it while the vehicle is in motion, because the airflows are dominated by that. Also, make sure that the operator doesn't have their window open. Just never, 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 never. Amid COVID, that regardless of what the vehicle is, even real slippery vehicles like Priuses, the air goes out the front window. It comes right back in the back one if that's open too. So we've got to be very careful. Close that driver's window, and it's counterintuitive, but ask them to take a piece of paper. If your employees balk at that, ask them to take a piece of paper and hold it up near that window when they're in a safe spot, like a freeway on-ramp or something. There's nothing to hit. And just a brief test, you'll be assured that that is drawing virus-laden air inevitably up toward you if you drive for any number of hours. So the bottom line, poor design imposes huge costs, both human and budgetary. Simple solutions are available, and the benefits far outweigh the costs of the change. And we need to think that through and vet all these things and triage the risks, but we can get there. And if agencies work together, we can force these blasted manufacturers who will come to you and say, well, we're not going to make any changes. You're such a small outfit. We just don't care. You've got to write us a huge check for all our costs if you want engineering changes. Baloney. If we get all the agencies together demanding competence, we're not demanding the moon, just competence. What's practical? We can have a far better tomorrow, and we can collaborate and work on that. And I'd love to see that done. Thank you.
Thanks so much, Brian. That's great. We've in the chat, we've put the resources, and the resources will be posted with this webinar on our YouTube channel within the week. And if you have any questions, please put them in the Q&A, and we'll respond to them. We asked Brian what he would recommend would be a first step. And first he said, we need to get together and demand what we need. But in the face of that, there are things that you might be able to do right now and things that are coming right up that might be helpful for both protecting your drivers' backs and their ability to work, and also, as you could tell from his explanation about the sheeting, really simple things that aren't real expensive can provide the barriers that you might need. So, Brian, if you wanted to ask or respond to the what could you do today?
Yeah, I think, again, triaging the risk of getting together, and this doesn't have to be an extensive effort, but just start making contact and sharing experiences and needs. That'd be great. I'd also urge that in that process, there's a very conscious effort to select employee representatives to be engaged with you on that, so that you get the experience of the frontline workers. This has been one of the key elements why airlines are safer, vastly safer at 6 miles up and 600 miles an hour than we are anywhere near a bus on the ground. You know, they traveled year after year, 700,000 millions of passenger miles without one fatality. And that's everybody getting together, thinking about these things, and that's frontline through management, through manufacturing. And we need to close that circle and work together on it. And those are the vital elements. Then we can triage the risk you see in your agency. So whether it's health, time loss, COVID, pedestrian safety, high-speed stability, these other questions we've gone through, we can triage those and knock them down one after another. And by collaborating together, the costs of those can just drop like a rock.
So as a starting point, if you haven't seen the cutter specification, you should check it out. It's available through the TRIPS program in Florida, and that is a safety tested specification. They have added the seat specification to that. So, and I have spoken with Lisa Stays at Cutter, and she is very open to us working with them to find other modifications that would be helpful. And so I think that our interest is in working with you to help identify what the things are. Oh, and look at Nellie has put the TRIPS Florida specification in the chat. And as I said, we've got these resources available that Nellie has put up there. We'll answer your questions if you have any more. And please take the survey. There's a QR code that is here, and you can just use your phone, take a picture, answer our questions, and tell us what you want to learn more of. I know the first time I saw this presentation, I just was freaked out, and I was like, oh my God, this is so incredible. But as we were talking about before we started, this is like 3 separate presentations, and we could go more into any one part of this to talk about it. And we really would like to help move this forward. I actually have spoken with the manufacturer and said, what could we do to improve buses? And he said, use the Florida specification. So that is a good starting point, and if you check that out, it's based on safety testing, which is not done at Altoona. Altoona is durability, and that's your warranties that the manufacturers have. Florida does safety testing, sled testing, rollover testing of the frame and the vehicle. So check it out. We'd love to hear from you. Thanks so much for everyone who stuck this out, and please take the survey. Thank you, Brian. You're the greatest.
Real pleasure, and thank you for putting up with the machine guns paced presentation.
Super. And I'm sure we'll see you again.
Yes, indeed.
Thank you.
Take care.